Hello and welcome. My name is Ashish Ahuja. I'm an applications engineer with Texas Instruments. Today we will talk about the USB module on the state-of-the-art brand new TM4C123X family of microcontrollers. By the end of this presentation, you will be familiar with the USB hardware and software on TM4C123X family of microcontrollers. To be more specific, we will discuss various USB modules and external signals. We will also take a look at the Tiva for C-Series USB library. In the end, I'll point you to resources where you can find more information and learn more about the details about USB peripheral on the TM4C123X devices. All of this material will equip you with the knowledge that will put you in a great position to begin developing your first USB application using TM4C123X devices. So let's get started. Let us take a look at the USB hardware first. USB is a standard that defines cables, connectors, and communication protocol used in bus for connection, communication, and power supply between various electronic and computing devices. Some of the key features of the USB are listed on the screen. It is a host-controlled communication protocol, that is, USB allows only one host and multiple devices per bus. USB also supports multiple data transmission speeds. It has evolved from USB 1.1 to 3 now. With the exception of USB 3, which uses 8 wires, USB uses 4-wire interface. One of the cool features of USB is the external hot swapping, also known as plug and play. It allows end users to connect and disconnect from the host while the bus is powered on. USB offers a low-cost data transmission and communication alternative because of the reasons we discussed. Wireless USB can be used for wireless data transmission. The TM4C123X family of microcontrollers feature an integrated USB controller with PHY. It operates as full-speed or low-speed function controller during point-to-point communication in USB host, device, and OTG mode. The controller complies with the USB 2.0 standard, which includes suspend and resume signaling. 16 endpoints, including 2 hardwired for control transfers, and 14 endpoints defined by firmware are supported. Also, there is a dedicated USB endpoint memory of 2 kilobytes with UDMA support. We will look at the USB module in more detail as we move along with this presentation. Let us take a look at the USB block diagram now. The USB module on TM4C123X devices consists of an integrated controller and PHY. The USB controller has an endpoint control block which receives and sends DMA requests from and to the DMA controller. The endpoint control block is connected to the FIFO RAM controller and packet encode and decode block. Packet encode decode block encodes and decodes the data packets sent or received from the USB transceiver macro cell synchronization block, also known as the UTM synchronization block. The function of this block is to synchronize between the transceiver macro cell and the function controller user supplied clock. The packet encoder and decoder block, which connects the UTM synchronization block to packet encoder decoder and endpoint control block, generates headers for the received packets. It also performs CRC generation and checking. The RAM controller provides an interface to a single block of synchronization RAM, which is used to buffer packets between the MCU and the USB. It takes the FIFO pointers from the endpoint controllers, converts them to address pointers within the RAM block, and generates RAM access signals. The FIFO RAM controller is connected to the CPU interface, which sends interrupts to the interrupt controller. USB requires at least 4 external signals to function: USB D+, D-, VCC, and ground. Sometimes USB ID and VBus are also required. USB D+ and D- are bidirectional differential data pins. Sometimes VBus signal is used during the session request protocol. It allows the USB PHY to both sense the voltage level of VBus and pull up VBus momentarily during VBus pulsing. USB ID signal senses the state of the USB ID pin on the connector. The USB PHY enables an integrated pull-up and an external element such as a USB connector to indicate the initial state of the USB controller. It allows support for the mini and micro size connectors, and its implementation in the USB controller allows it to support true OTG functions as well. USB power fault signal is used as an option in the host mode by an external power source to indicate an error state by that power source. USB power enable signal is optionally used in the host mode to control an external power source to supply power to the USB bus. Required signals go in an actual connector on the board and have fixed pin assignments. The USB module on TM4C123X family of devices supports 3 modes of operation: host mode, device mode, and on-the-go mode. Host mode allows TM4C123X devices to interact with USB devices such as flash drives. The host mode allows the users to use a USB mouse or a keyboard as an input to your TM4C123X device. Host mode also allows firmware updates to the microcontroller via flash drives, eliminating the need of PC altogether using the USB device firmware upgrade class. Device mode allows TM4C123X microcontrollers to connect to the USB hosts such as computers. The microcontroller can be powered over the USB bus, eliminating the need for an external power supply. When the microcontroller is in the host mode, it allows PC side applications to perform firmware updates over USB OTG mode. OTG modes facilitates dynamic switching between the host and the device modes. The USB connector on the evaluation kits can be used to connect both the host and the device cables. Okay, so far we talked about the hardware features of the USB module on TM4C123X micros. Now let us take a look at the software that makes USB on TM4C123X microcontrollers so convenient and easy to use. It's TivaWare for C-Series. TivaWare for C-Series is an extensive suite of software designed to simplify and speed up embedded application development using Tiva C-Series microcontrollers. TivaWare for C-Series includes peripheral driver library, graphics library, USB library, and sensor library, which includes several APIs to configure and initialize different peripherals on the Tiva C-Series microcontrollers. These libraries come with the source code, which is mostly in C. They're all pre-compiled for use as is and can also be adapted as desired. TivaWare for C-Series also includes bootloader, several code examples, and third-party packages that allow you to focus on your application development and not so much on how to set up the microcontroller. TivaWare for C-Series USB library is a set of data types and functions for initializing and configuring the USB module in the host, device, and OTG modes on the TM4C123X microcontrollers. It consists of free, license, and royalty-free drivers with example applications to accelerate USB implementation on TM4C123X devices. The capabilities and the organization of the USB library functions are governed by the design goals such that it must be written entirely in C and should be fairly easy to use. The library functions are easy to understand and are reasonably efficient in terms of memory and processor usage. The USB library can be built with more than one tool chain. The USB library is built over DriverLab APIs to provide a higher level support for USB. This includes implementations of common USB classes as well. The layered structure of USB library means that developers can choose to the extent to which they use library functions. To speed up and ease application development, a number of examples for each of the 3 modes, namely host, device, and OTG are also provided. TI is a member of USB Implementers Forum. This shows our strong commitment towards USB in not only the current TM4C123X family of devices, but also the ones going forward. The USB library contains USB class-specific source files and header files which contain function definition and declaration for over 175 APIs. These files are located in the designated folders in TivaWare for C-Series. We also provide compiler-specific pre-compiled libraries for different tool chains. These pre-compiled libraries are located in the respective directories of each tool chain. The directory paths are shown on the screen. Inside the USB library folder, the USB device specific and host specific files are located in device and host folders. Now let's take a look at the different USB classes. USB Human Device Interface class is a part of USB specification for human interface devices such as keyboards, mice, game controllers, and alphanumeric displays. The USB HID class is defined in a number of documents provided by the USB Implementers Forum's Device Working Group. The primary document used to describe the USB HID class is the Device Class Definition for HID 1.11. This class allows the development of a USB device without a custom driver for native Windows support. Many predefined functions exist in the USB HID class. These functions allow hardware manufacturers to design a product to the USB HID class specification and expect it to work with any software that also meets these specifications. One of the other most commonly used USB classes is the USB Device Firmware Upgrade class. It is an official USB device classification of the USB Implementers Forum. It specifies a vendor and a device-independent way of updating the firmware of the USB device. The idea is to have only one vendor-independent firmware upgrade tool as a part of the operating system, which can then be downloaded into the device. In addition to the firmware download, it also specifies firmware upload, that is, loading the currently installed device firmware to the USB host. USB DFU class offers a more versatile USB bootloader, which is available in the Tiva for C series. USB device firmware update is also available in ROM of some TM4C123X devices, so you can just plug in the device and reprogram your firmware. You can refer to the USB bootloader example provided in Tiva for C series to see for yourself how you can utilize USB library APIs in your application to upgrade firmware using the DFU class. Now, let us take a look at the USB Communications Device class, also known as CDC. CDC is generally implemented in embedded systems like mobile phones to achieve more than one functionality from the device, so that a phone may be used as a modem or a fax or a network port. This class provides simple serial communication functionality. You can refer to the USB CDC serial example in Tiva for C series as a starting point for more complex serial communication and file transfers. The data interfaces are generally used to perform bulk data transfer using bulk USB device. There is an example program in Tiva for C series, which is a simple data echoing app. It serves as a basis for more complicated data transferring applications. One of the benefits of a well-defined specification like the USB HID class is the abundance of device drivers available in most modern operating systems. The USB HID class devices and their basic functions are defined in USB Implementers Forum documentation without any specific software in mind. Because of these generic descriptions, it is easy for operating system designers to include functioning drivers for devices such as keyboards, mice, and other generic human interface devices. The inclusion of these generic drivers allows for faster deployment of devices and easier installation by end users. There are several example applications in Tiva for C series that can be good starting points for supporting other HID devices. The USB mass storage device class allows an application to act as a physical storage device for use by other USB applications or for a host operating system. Because the type of storage can vary by application, the mass storage class abstracts the storage within a set of block-based APIs that are provided by the application to the USB library. The APIs in mass storage class allow the USB mass storage class to call an external set of functions that actually perform the operations on the physical storage media. The USB library's mass storage class also provides an interface to inform the USB library when the media status has changed in the case physical media can be ejected. This is important for devices like SD cards that can be removed before the device is connected or even when the device is running. There are about 125 APIs in the USB library, and for further clarification, they can be classified into 4 key categories or levels. Each category indicates the level of abstraction that API provides to the end user. At the top layer of the USB library, there are application interfaces that provide easy access to the various types of peripherals that are supported by the USB library. Below this layer are the USB host controller device interfaces that handle the specifics of each type of device and how to communicate with the USB host class driver. USB library is a set of data types and functions for creating USB device, host, and on-the-go applications on TM4C123X family of microcontrollers. The contents of the USB library and its associated header files fall into four main groups. General purpose functions used by both device and host applications. These include functions to parse USB descriptors and set the operating mode of the application. Device-specific functions providing the class-independent features required by all USB device applications, such as host connection signaling and responding to standard descriptor requests. Host-specific functions providing class-independent features required by all USB host applications, such as device detection and enumeration and endpoint management. Class-specific functions and data types to aid development of applications conforming to several commonly used USB classes. The advantage to this structure is that the developer can modify a complete, very specific USB application to handle a new feature, or create a completely new application based on the examples while retaining the advantage of already written code in both cases. Which API to use when? With so many APIs, it can be overwhelming to determine which APIs to use when. The answer depends on the level of abstraction that is most suitable for your end application. Let us take a look at this slide in order to understand this a little bit better. Some example USB applications are listed in red blocks. Each application requires different levels of customization. Application 1 is highly customized and implements its own USB protocol, that is a third-party USB stack, whereas application 4 is relatively standard and passes data to higher-level APIs in a custom HID mouse. Different layers or levels of abstractions are listed in the black blocks. For an application that involves passing simplified data to a higher level API, using host or device class APIs is the recommended approach. This provides the highest level of abstraction and speeds up the development. This is represented in application 1 in the diagram on the slide. For an application that involves implementing its own USB protocol using driver lib, working with USB driver API is the recommended approach. This provides the lowest level of abstraction, giving the user the most amount of visibility and control. This is represented in the application 4 in the diagram on the slide. For applications in between, like examples 2 and 3, a user can pick and choose a level of abstraction that is not too high or too low. This is how applications fit into the API system. Note that devices that resemble existing applications require significantly less code. To conclude what you have learned so far, TM4C123X devices continue to deliver a strong value proposition and offer strong differentiation with its USB module, which supports host, device, and OTG modes of operation. To speed the application development involving USB, a number of USB APIs and code examples for multiple device classes are provided in Tivaware for C-Series. We have an extensive repository of excellent documentation including device datasheets, user manuals, application notes, etc. that have been created to strengthen your understanding of TM4C123X devices and to accelerate design and development of your projects. If you have any technical questions, you can contact Tiva C-Series experts on the TI E2E forum. Please visit ti.com/tiva-c for technical documents, samples, tools and software, and e2e.ti.com to obtain technical guidance. Good luck with your first USB project. Stay tuned and keep innovating with TM4C123X devices.